definitely include as many do-it-yourself things to just the exact recipe because it seems like it's fairly straightforward in the implementation side. And then also include a little bit in thinking about the cleaning cycle. Because I think it becomes obvious then, oh, what is the cost of, what is the lifetime of this? Because there's no consumables. Currently, there seems to be that this is a technique that has no consumables, but you should prove that in the context of how is it used. Okay, is that you, Meher? Take it away.
Yes. Yeah, yeah. Just a second. We are sharing our screen.
Roger.
Yeah, I'll send an email about the final deliverables class.
Okay.
It'll consist of, yes, it's showing slides and also uploading on the wiki site.
Okay. Yeah, I think the documents should all be on Wiki because then I can go through everything.
Yeah.
Is our screen visible?
Yeah, we can see it. Go ahead, Meher. Yeah.
Yeah. So good morning and good evening, everyone. I'm Mayank
And I'm Mihir.
and we are from Asoka University. And today we are presenting Uplift 21, a frugal AI-assisted ultrasound screening framework designed to improve prenatal detection of trisomy 21 or Down syndrome, particularly resource-constrained healthcare settings across India. Trisomy 21 is the most common chromosomal anomaly worldwide. It occurs when a fetus carries an additional copy of chromosome 21 and as is associated with conditions such as congenital health defects, gastrointestinal abnormalities, and development delays. Globally, the probability of Down syndrome increases significantly with maternal age, making prenatal screening especially important. The critical screening window occurs during the first trimester between 11 and 14 weeks, where clinicians measure specific sonographic soft biomarkers, particularly nuchal translucency thickness. Detecting abnormalities during these windows allows clinicians to guide further diagnostic testing and clinical planning. However, the main challenge in prenatal screening is not detecting markers, it is interpreting them correctly. India sees around 26 million annual pregnancies every year, and ultrasound machines are increasingly available across district hospitals and primary healthcare. But interpreting subtle biomarkers like nuchal translucency thickness requires highly specialized training. As a result, the healthcare system faces a major interpretation bottleneck. The key insights behind our work is the bottleneck is in prenatal screening is not hardware availability, it is expert interpretation of the biomarker. And Uplift 21 addresses this by introducing a model that assists clinicians in interpreting screening markers more reliably. India's prenatal healthcare system operates at enormous scale. With approximately 26 billion births annually, the demand for prenatal screening is extremely high, but is resource constrained. At the same time, nearly 65% of the population lives in rural areas where access to advanced maternal healthcare infrastructure is limited. Certified fetal medicine specialists are concentrated in urban centers, which creates a major gap between the availability of ultrasound hardware and the availability of expert interpretation. This disparity is where our improved trial system can have the greatest impact. And so, when screening suggests this is our current golden standard in India. So when screening suggests elevated risks, confirmatory testing is required. So the most accurate option is NIPT. That is a blood test, a non-invasive blood test with over 99% accuracy, but it costs around 150 to $300, making it inaccessible for many families in India. Another option is amniocentesis, which provides definitive diagnosis but carries a miscarriage risk of around 1% and requires specialized facilities and specialized doctors in this. And then comes the ultrasound screening on the other hand, and is inexpensive and widely available. However, its accuracy depends heavily on expert interpretations of the result. Therefore, improving risk trials at the screening stage becomes critically important. So, our approach builds directly on established medical research. So a 2025 umbrella review by Gotterdzi and colleagues shows that combined ultrasound and serum screening can achieve over 93% sensitivity and 95% specificity. At the same time, machine learning research such as the Yelchin et al. 2025 demonstrates that gradient boosting models can reach around 95% accuracy for Down syndrome risk prediction. So Uplift 21 especially digitizes its validated screening protocols into an accessible AI-based decision support tool.
Uh, Uplift 21 introduces a 7-feature numerical decision layer that operates on standard first trimester screening markers. These inputs include nuchal translucency thickness, nasal bone presence, fetal heart rate, maternal age, crown rump length, beta HCG MOM, and PAPP AMOM. These features are processed through an ensemble gradient boosting model trained on clinically realistic data distributions. Instead of producing a simple binary output, the model generates a three-class probabilistic risk stratification, low, moderate, or high risk. This allows clinicians to triage patients more accurately before recommending costly or invasive confirmatory tests. A core design goal of Uplift 21 is frugal deployment. Many AI healthcare systems require cloud infrastructure or specialized hardware. Uplift 21 does not. The model runs locally and requires no GPUs, no cloud connectivity, and no specialized infrastructure. This allows it to operate directly within primary healthcare centers where most early prenatal scans occur. Additionally, we integrate SHAP-based explainability, which allows clinicians to see exactly which clinical features contributed to each prediction. Slide. Our deployment model aligns with India's existing healthcare structure. At the village level, community health workers encourage early prenatal screening. At the community health centers, clinicians perform ultrasound scans and use Uplift 21 to assess risk. Only cases flagged as high risk are referred upward to district hospitals for confirmatory diagnostics such as NIPT or amniocentesis. This targeted referral system preserves hospital capacity while improving access to specialized care. Next slide. It is important to emphasize that Uplift 21 is a decision support system, not a diagnostic tool. The current prototype is trained on synthetic clinical distributions, which allowed us to design and evaluate the system architecture safely. However, the model does not yet incorporate factors such as ethnicity specific biochemical medians, twin pregnancies, or maybe IVF cases. Future developments will focus on validating the system using institutional clinical data sets. Now, we evaluated several tree-based machine learning models, including Random Forest, XGBoost, Light GBM, and CatBoost. These models perform extremely well on structural clinical data. Our experiments achieved ROC AUC values above 0.97, demonstrating strong predictive performance across risk classes. These results confirm that gradient boosting approaches are particularly well suited for prenatal screening risk stratification. Now, deploying a system like this in India's public healthcare system requires addressing three key constraints. First is hardware limitations. Many primary health centers operate legacy ultrasound machines, so the system must remain hardware agnostic and compatible with the existing devices. Second, software performance. The model must run through edge computing, meaning inference occurs locally without requiring internet connectivity. Third, regulatory compliance. India's PCPNDT Act prohibits fetal sex determination, so the system must be designed to enforce compliance by preventing extraction of identifying features related to fetal sex. These constraints guided the design of Uplift 21 from the beginning. Next. We also considered several potential risks. First, dataset bias. To address this, we plan to build localized datasets through collaborations with Indian public hospitals. Second, ultrasound imaging variability. We use synthetic augmentation techniques to train the model to recognize anatomical patterns rather than machine specific artifacts. Third is legal compliance under the PCP and DT Act, like I said earlier, which we address through hard coded anatomical masking. Finally, we implement a human in the loop system, ensuring clinicians retain full control over final measurements and decisions. Now, Finally, our goal is to democratize expert level prenatal screening. Uplift 21 shows how lightweight AI systems can strengthen existing healthcare infrastructure rather than replacing it. By improving triage at the earliest stage of screening, we can reduce unnecessary procedures, lower healthcare costs, and ensure that a patient's geographic location does not determine the quality of her prenatal care. Now, I'll walk you through our current prototype. Okay, just a second.
That was fantastic and on time as well. So I'm excited to see the demo.
Yeah. Can you see my screen?
It's loading now. Yeah, we see
Yes.
it now.
Yeah. So this is the current prototype. This is where we put in the 7 parameters, and let's run the assessment. So this is where it shows the dominant risk probability, all three of them, low, moderate, and high. And based on the probability, we have a clinical recommendation and a model explanation using SHAP. And there's also this button to download this clinical report as a PDF. So get this as a PDF report.
And then Mihir, if you go back to the demo, can we just open to questions now, unless you were going to share something else? Time for
Not
questions?
really. I don't have anything else, but
Okay.
we had a meeting with KCD yesterday,
Yeah.
which is Koeta Center for Digital Health here at Ashoka.
Yes.
And we talked to them about data since they have connections with Max Healthcare in
Yeah.
Delhi.
Yeah.
And we have set up a meeting with the director next week. So
Yeah.
yeah,
No, I think Anurag would be a perfect person to talk through with this,
right, right.
especially because, I mean, yeah, Ashoka has a phenomenal infrastructure. Honey had a technical question, so I'll let her ask that, and then we'll jump back to more general questions. Honey, go ahead.
Okay.
Yes, so I just wanted to understand that did you check for the test ROC that you mentioned it is the ROC was coming 0.97 if I'm right, and it is
Right.
pretty highly accurate. And did you check for precision and recall? Like, did you check that?
Yeah, we did.
Okay, so what was the test ROC like that you get for this model?
Can you repeat?
What was the test ROC? So did you, when you mentioned ROC, did you also measure the test ROC or other parameters like precision and recall to understand the class imbalance? Or because accuracy, sometimes the model can be really accurate, but it could
Mm-hmm.
have highly imbalanced data set. So yes, did you, and it may
Yeah.
not work that well for the
Our
data.
test ROC was somewhere around 0.90.
Okay,
Uh,
that's
and
good.
Maybe just to better understand, I missed this point. Where is this data coming? Is the data completely synthetic at this point?
yeah, it is.
Everything.
Yeah,
Yeah.
that's what.
Okay.
Okay.
6,000 samples as of now.
Yeah, but it's 6,000 synthetic samples, or are they
Yeah.
actual samples? No.
No,
Those are
there's synthetic
synthetic sample.
ones.
Yeah,
Okay. And
that's
the synthetic samples, is there a synthetic database also for ultrasound images? Because two of the
Yeah,
features were image-based, and there
there
are
is
synthetic.
one,
Yeah,
like I discussed in the first meeting we had, there is one on Dataset Ninja, but it
I
is
see.
not specific to Down syndrome, and we are currently not training the ML model on images. We are currently doing it on image data, right?
Got it. Got it.
Yeah.
Okay.
Got it. Yeah, yeah. Other questions, comments? Actually, one thing I wanted to bring up, which is very India specific, is the masking. Because
Right.
for most people on the call probably already know this, but in India, detecting gender of an unborn child is illegal. So how far has masking technology already is in the market? Do you know of an example where ultrasound is because handheld ultrasound has become available, but it's actually illegal for many healthcare workers to use ultrasound currently if they are not the certified radiologist. So,
Right.
and there has been this talk about masking for gender, that you could not use it to detect gender, but I don't know how much of that is implemented already. I'm just interested in, like, the number of places that you said had ultrasound. Are they also have certified the ultrasound technicians that are allowed to do this?
That is something to look upon.
Yeah, I think it would be very valuable to see, because I know the Gates Foundation has invested a significant amount. Weber, did you want to add to that? Weber, you're muted.
You're on mute.
You're still muted, Weber. We have to figure out how to unmute you so you can give the talk. Okay, we will unmute you.
I can.
Ask to unmute. Okay, does something pop on your end? Oh,
Okay.
are you unmute now? Try it now.
Yeah. Can you hear me?
We can hear you. Yes.
Okay, so yeah, I was saying the implementation of the masking law is really strong in India. And there are some instances where people would go to countries abroad like Thailand
Yeah.
and to bypass the laws. But in India, even if you go to rural laboratories, even there, masking is
Yeah.
done.
Yeah. But what I just meant to say was whether it's algorithmically done or is it done by people? I know the laws are very strict, so it works. But the notion is to think about whether the current instruments can handle that algorithmically. So that way, other tools and other utility of ultrasound could be much broader.
No, it is, I think, people level. So the
People level,
clinics
that's what
and
I
people
understood.
level.
Yeah,
Yes.
yeah. But I think it would be nice if it became computational, then a broader group of people could be allowed to do. Yeah, no, this is fantastic. And the fact that you already spoke to the Quota Center, that gives you a sense. I think the most important thing to do would be is to switch to finding data sets. That's going to be the key, because as a problem, it's a very clean, sharp, very focused. Okay, Weber, let's switch. That would be the